Today we're going to talk about applications of both exponential and logarithmic equations. We're going to start with word problems where formulas are given to you, and then we'll also look at problems where the formula is not given to you. So let's start with word problems where formulas are given to you. So here's the first example. Estimates of the world population in millions from 1992 through 2000 are shown in the table. An exponential growth model that approximates this data is p equals 5303 e to the 0.013838 t, where t is between 2 and 10. P is the population in millions, and t equals 2 represents 1992. According to this model, what year corresponds to a world population of 6.5 billion? Now for this problem, we want to just make sure we know what everything represents, and we want to make sure we know what the units are. So looking at the formula that's given to us, it tells us that P is going to be the population in millions, and then T is basically the year since 1990. So if T equals 2 represents 1992, then the year 1996 is going to be T equals 6. We get to 2000, that will be T equals 10. It will be 10 years after 1990. So 6.5 billion, we want to write that in millions. So in millions, that's 6,500 million. So let's replace P with 6,500. We're trying to find out the amount of time it takes, or what year it corresponds to that population. So now we can go about solving for T. So we'll apply everything we know about how to solve an exponential equation. So let's isolate the e to the 0.013838 t. So divide both sides by 5303. And then we'll take natural log of both sides. And now we use the power law, move that 0.013838 t out in front. The ln of e cancels. And now we solve for t, so divide both sides by that 0.013838. This gives us that t is about 14.7, which means 14 years after 1990 would correspond to 2004. Now, I know it's unclear whether this population is starting at the beginning of that year or corresponding to the end of that year. But if we were saying it corresponds to the beginning of that year, the population at the beginning of the year 1992 is 5,445 million, then here we're saying that in the year 2004, sometime during that year, not at the beginning, but much later on during the year, but about 0.7 of the way through the year 2004, the population will hit 6,500 million or 6.5 billion. Let's look at example 2. On a college campus of 5,000 students, one student returns from vacation with a contagious flu virus. The spread of the virus is modeled by the following equation, where y is the total number infected after t days. The college will cancel classes when 40% or more of the students are ill. Part A, how many students are infected after 5 days? And then part B, after how many days will the college cancel classes? Okay, so remember that y, we're told, represents the total number of infected students. T represents the number of days. Now, how many students are infected after 5 days? That means when t equals 5, what is y equal to? So this is just a matter of plugging it right into the formula. When you put this into the calculator, make sure you put that entire denominator in parentheses. This should come out to be about 54 students. Now, for part B, you're asked, after how many days will the college cancel classes? Well, you're told the college will cancel classes when 40% or more of the students are ill. Now you're told that the college campus has 5,000 students, so we want to know when will it hit 40% of the population. So For y, we want to know what is 40% of 5,000. So that's going to be 0.4 times 5,000 equals, and then 5,000 over 1 plus 4999 e to the negative 0.8t. We need to solve for t, right, after how many days? Okay, so 0.4 times 5,000, that's going to be 2,000 students. And now we need to get that exponential out of the denominator and then by itself. So I'm going to start by multiplying both sides by that denominator. Okay, now I'll divide both sides by 2,000. That actually simplifies our problem a bit. And then we're going to subtract 1 from both sides. And then now I'm going to divide by 4,999. Now we have the exponential portion by itself. So now I can take the log of both sides, natural log ln of both sides. Move the negative 0.8t out in front. Ln of e cancels. And get t by itself, so divide that by negative 0.8. Okay, putting that entire thing into the calculator, we should get that the approximate amount of time that it takes is about 10, so 10 days. Okay, now what if a formula is not given to you in an example? So when a formula is not given to you, then you can use the general exponential growth or decay model. So A equals P times e to the RT. This is also the formula for calculating interest compounded continuously. If you get a problem where interest is not compounded continuously, it's compounded quarterly or compounded monthly, there's a different formula for that. But if you're told that the interest is compounded continuously, same formula. Okay, take a look at example 3. If a $500 certificate of deposit earns 4.25% interest compounded continuously, then how much will be accumulated at the end of a 3-year period? So let's start by using the formula and plugging in what we know. So the initial amount is $500, right? $500 certificate of deposit. And the rate is 4.25%. Make sure that when you plug the rate in, you put it in as a decimal. So 4.25 is going to be 0.0425. And then the amount of time that passes is 3 years. Make sure when you simplify this that you do e to the 0.0425 times 3 first before you multiply by 500. This should come out to be about $567.99. Okay, example 4. How long does it take to double an investment at an annual interest rate of 6.35% compounded continuously? Here's the formula. And now, you're actually not told what the initial amount is. What you want to know is how long is it going to take to double? So if you start off with some amount p, for that investment to double, you'll have 2 times p. So we'll replace a with 2p, and then we'll plug in the rate. Now it seems that we still have 2 variables here, but because there's a p on either side, we can cancel that out. So 2 equals e to the 0.0635t. And now, since we have the exponential actually already by itself on the right, we can take the log of both sides. So we have ln of 2 equals ln of e to the 0.0635t. Use the power law, move the exponent out in front. Ln of e is equal to 1. And solve for t. So divide both sides by 0.0635. So ln of 2 divided by 0.0635 comes out to be about 10.9 years or so. So it actually doesn't matter how much you're investing. If you just want to know how long it's going to take to double that investment, it's still going to take about 10.9 years. Okay, example 5. A certain bacteria has an exponential growth rate of 25% per day. If we start with 0.5 grams and provide unlimited resources, how much bacteria can we grow in 2 weeks? Alright, so no formula given. Let's use the part equation here. So the amount we start with is 0.5 grams, so P will be 0.5. And then the rate is 25% per day, so that's going to be 0.25. Now notice that the rate is given as a percent per day. So make sure when you plug in for T, you're plugging in days. So it's asking how much bacteria can we grow in 2 weeks? That's equal to 14 days. So make sure you put 14 in there. So always the rate and the time should correspond with each other. If the rate is per day, then the time should be the number of days. If the rate is per year, then the time should be the number of years. Okay, so that comes out to be about 16.56 grams. Now, read the question carefully. It said, how much bacteria can we grow in 2 weeks? Now, we started off with 0.5 grams, so we did not grow that 0.5 grams. But in the end, we have 16.56 grams. So we just want to subtract out the amount that we started with, and whatever's left is how much we grew. So 16.56 minus 0.5 comes out to be 16.06 grams. All right, example 6. During its exponential growth phase, a certain bacteria can grow from 5,000 cells to 12,000 cells in 10 hours. At this rate, how many cells will be present after 36 hours? So first, what's the rate? You're not actually told what the rate is. So this is actually what I call a two-part problem, because first you're going to have to use the information given to figure out what the rate is. Once you've found the rate, then you can find what it's actually asking you for. So how do we figure out what the rate is? Well, we know that it grows from 5,000 to 12,000 in 10 hours. That gives us everything in the equation except for R. So let's plug that in. So we start off with 5,000 and then we get to 12,000 after 10 hours. Alright, we'll divide both sides by 5,000. So we get 2.4 on the left. Take natural log of both sides. Move the 10R in front of ln of e. ln of e is equal to 1. And solve for r, so we have ln of 2.4 divided by 10. Now I'm going to leave this answer like this. It's more exact right now. And since we haven't actually gotten to solve for what the problem is asking for, let's try to keep everything as exact as possible until we can approximate at the end. So now we solve for the rate. So now we go back to this equation and we want to know how many cells will be present after 36 hours. So we're still starting with 5,000 cells. We know after 10 hours it's 12,000 cells, but we want to know how many cells will be present after 36 hours. So this is going to be 5,000 times e to the, and then we'll plug in for the rate that we just found, and then multiply that by 36. Make sure you deal with the exponent first before you multiply by 5,000, and you should get an answer that's approximately 116,877 cells. Okay, one last example. A certain isotope has a half-life of 4.2 days. How long will it take for a 150 milligram sample to decay so that only 10 milligrams are left? Okay, so this is sort of similar to the last example where we have two parts. We're going to need to figure out what the rate is. And then after we figure out the rate, then we can actually solve for what it's asking for. So first, what's the rate? Well, we know that this isotope has a half-life of 4.2 days. What does that mean? That means however much you start with, you'll end up with half of that after 4.2 days. So if we start with P, we'll end up with 1/2 of P. after, and then you can replace t with 4.2. The p's cancel from both sides, and now we can solve for r. So take natural log of both sides. Move the 4.2r using the power law out in front. Ln of e cancels. We divide by 4.2 to solve for r. Again, I'm going to leave this in this form, just so it's a more exact answer when we get to the second part. So now we solve for the rate. Now it's asking us how long will it take for a 150 milligram sample to decay so that only 10 milligrams are left. So let's plug in what we do know. We start with 150, and we're left with 10. The rate we just found, and now we know we have to solve for t. All right, let's go ahead and get that e to the ln of 0.5 over 4.2t all by itself. So we'll divide both sides by 150. Okay, now we take log of both sides, move the ln of 0.5 over 4.2t in front. Ln of e is equal to 1. And now we solve for t. So now to solve for t, we can divide both sides by this giant fraction here. So divide ln of 1/15 divided by ln of 0.5 over 4.2. Okay, and if we were to find the approximate value here, it should come out to be about 16.4 days. And you can also double check for yourself, does this answer make sense? Well, we know after 4.2 days, from 150 it becomes half of that, so it becomes 75. After another 4.2 days, it's half of 75. And you can continue doing that, and you'll end up finding it'll take about 16 days for it to get down to 10.